good evening. Today, we're going to talk about a project which is flood behavior and watershed intelligence system. This this project is built on LiDAR and it aims to make a water simulation system that can predict when a flood is going to happen before it actually happens, and it is better than the data that we get from the current system, which is based on geospatial data. So let's see how it goes. First, let's talk about why this matters in India. The problem statement, how, what is the specific district we are targeting. For this particular study, we have ran this model on the state of Bhagalpur in Bihar, but the model is built in a modular way in which you can enter the LiDAR data that is publicly available and put it into the data folder of our system, and it will automatically generate the same processing that it did for this pre-rendered state. So why this matters in India? As we know, global warming is increasing, and as global warming is increasing, more and more rain comes in. Abrupt rain comes in. Now, say a river is flowing, and like sudden rain happens. This leads to flash flood. The people that are living in a certain vicinity of the river or the water source or in the basin itself will not have adequate time to go and reach out to basically evacuate the area. The perfect example of this is the Kosi incident, which happened in 2008. The critical gap is that the flood maps that we have right now are based on geospatial data. Now, the thing with the geospatial data is that it tells you the range for plus 3 and minus 3, meaning that the error can be plus 3 minus 3. This doesn't sound plus 3 minus 3 meters. This doesn't sound that huge of a difference, but it almost equate to a wall size. So this wall, the top point and bottom point will be equal in geospatial. Now, because the height of a human is much lesser than that, it is very difficult to predict when the flood is actually gonna happen before 8 hours using the traditional systems. Now let's talk about the solution we built. So the major discrepancy that we identified was the use of geospatial data, and we solved it by changing the data source itself. As we know that the government is actively promoting use of LiDAR data, and it is aimed that by 2030 the entire India will be mapped by LiDAR and will of course be publicly available. Now, the special thing about LiDAR is that LiDAR tells you the specific coordinate of a point, meaning that the margin of error is plus minus 2 centimeters. Compare that to the 3 centimeters of the geospatial to this 2 centimeter. What this means for us is that we will be able to tell a lot before 8 hours, which is the current time when flood alerts happen, when the flood is gonna happen. The model that we have built works takes rain as an input parameter, the percentage, the chances of rain happening in a particular place happening, take that as an input parameter to calculate the percentage of the chances of rain that is gonna happen. Meaning that if I have data for say the next 1 week, how much is that? In 1 week, as I get closer to my date, the accuracy will keep on growing because the weather data will keep on growing. We know that it is very hard to predict rain, especially in monsoon season in certain parts of India. That's why we have another layer, another AI layer to this, which I'll explain when I explain the role of AI in this project. Now, let's take a quick look at the pathway that we are following. So we have the LiDAR data which tells us the 3D coordinates of each point. What we get from that is the elevation map of the entire system. I'll later show you the prototype. Actually, the prototype is just right here. Basically, from each point we are simulating an elevation curve, taking elevation. From the elevation we are deriving certain parameters. These are slope, aspect and curvature. Then from there on, we are obviously, because water flows downwards, we are using D8 algorithm to basically calculate when the water is gonna flow and how it's gonna flow, and that's how we are simulating river. And the advantage of this system is that if rain is gonna happen at place X, its effect will obviously be felt at place Y. This is a factor that is not normally considered and taken much into account in traditional systems, and that's where the beauty of LiDAR actually shines. So we can accurately predict what's going to happen at place Y based on the rain data of place X. Now, this Y say that it has multiple rain sources x1, x2, x3, x4. That just continues on increasing the probability of what the actual percentage of flood will be here. So that is how we are doing things in simpler terms. There are two main things that are the downfall of LiDAR. First, LiDAR can't tell you how much the land absorbs. Okay. Yeah. Two things. First, the LiDAR can't tell you how much water will be land absorbs. That means how much there's the perception and the water that's taken by the trees. Second, LiDAR can't tell you the depth of a river, or like how much water is gonna be held into the river. To combat these problems, this is where the role of AI comes in. We are using AI to take two parameters. These parameters are one, an absorbance coefficient, and second, a water level coefficient. Now these two coefficients are not known, like are unknown. We can't tell them by the current data. So we took the data that is available for the past 50 years on the internet, obviously published by government websites. We ran an AI model on them, used our system as base, and calculated the approximate value for particular chunks of the intended region, which is the Bhagalpur region of Bihar. That is the role of AI, and that is how we are using AI to combat the problem of LiDAR in this particular scenario. Next is the district relevance and how it's gonna actually help. So, as we said that the current system uses eight alerts 8 hours before. What we are expecting the system to do is to approximately tell you 2 days before, that is 48 hours, which is more than 200% increase with surety, and 1 week before, when the rain data comes in of various places, we can start predicting to a very accurate degree. That's where this system shines. Inclusion and cost effectiveness, because this is a tool that is meant to be used by government, and the computing power isn't that much, because we aren't using real time AI, which actually takes a lot of space. Rather, the entire processing that is done in two sets: the static part and the dynamic part. The static part includes the virtual elevation, the virtual mapping of LiDAR, which will take some hardware but is like a one time thing. The only dynamic part of the system is the rainfall data, which of course won't take that much compute power out of the system. Hence, why making the entire system very cost efficient to use on almost a daily basis. Okay, these are some of the processing. These are some of the results that we got. So for a particular area, this is the low rain, medium rain, and when the rain is too exclusive, too much. And let me put it light in. Yes, that should do it. A bit of issue with light, but and let me just demonstrate the system. My part is just this much right now. Let's see. So as you can see that this is a system, and right now the intensity is 0 and the duration is 0. If I increase the intensity, certain parts, see this region, which is like mapped by a different color, is showing a particular flood risk. Now this flood risk is just not coloring on the map, it is actually computing in backend and running a mini water simulation system of what's going to happen as described earlier. Let's say I increase the wait duration. By the way, this the place that we're increasing the water right now is locally, but we do have the option to do it at a specific place too. So this was a system. I hope you liked it, and yes.